Simple harmonic motion and energy conservation. The figure shows a mass oscillating in simple harmonic motion. Circle the type or types of energy the system has for each location of M. Then write an equation expressing the total energy at that point. When the displacement is negative A, so when we're all the way over here, we've got elastic potential energy but no kinetic. The total amount of energy is going to be 1/2 kx squared. Well, that's essentially that. If you square negative A, you still get a positive value. At x equals 0, we have no elastic potential energy, but only kinetic. 1/2 m, and won't the speed be a maximum there? We could write v max squared if we wanted. How about at x is equal to x? Well, you can see in my picture here that when x is equal to x, we're not at the extreme points, but we're not at equilibrium either, which means we have some elastic potential energy in there, but we also have some kinetic. We're going to say the elastic potential energy would be 1/2 kx squared, and the kinetic energy would be 1/2 mv squared. And lastly, when we're at the extreme point, we have entirely elastic and no kinetic energy. So that would be the same as that first one that we found, 1/2 ka squared. And if mu sub k is equal to 0, we're going to assume that mechanical energy is conserved. And so what that means is all of these are equal. This amount is equal to that amount, is equal to that amount, is equal to that amount. And if we know the amplitude, we can calculate that right off the bat. And then that amount of energy then in between the extreme points is divvied up between elastic potential and kinetic. All right, let's try this then. In terms of K, A, M, and V, derive an expression for the position x, where the mass has the speed v. The total energy, we just said, is numerically equal to 1/2 k amplitude squared. That's the total amount of energy. And at some random location, it's going to have some elastic potential energy, and it's going to have some kinetic energy. So let's see if we can derive an expression for x here. I'm going to multiply both sides by 2, so the 1/2s will go away. And to solve this for x, it looks like we want to subtract mv squared from both sides, divide both sides by k, and take the square root. You check and make sure I'm doing this correctly. If I want to factor out the k, I can do that. That'd be perfectly fine to do that. You want to leave the k's in there, that's fine. You want to put the k just under the fraction of the mv squared, and then just leave a squared by itself out here, that's okay too. All right, letter D. Show that part C gives us one or more recognizable locations x when v equals 0. V equals 0, that means I put a 0 there, and then what's left but k amplitude squared divided by k? Well, that means amplitude squared underneath the square root sign, and that would be x is equal to plus or minus a. Yay, looks good. How about letter E? In terms of A, X, M, and K, derive an expression for V when the mass is at location X. So we're going to do essentially the same thing here, except we're going to solve the equation for V instead. So let's go back up to the top. It would be the same equation. If we were solving this for V, wouldn't we take this kx squared term and put it on the left where it would become negative, divide by m, and then take the square root. You check and see if then this comes out okay. We're going to subtract. I'm going to factor out the k then too. Okay, a squared minus x squared divided by m square rooted. Let's check our work up to this point by plugging part D into part E. Well, in part D, let's put x is equal to a in there. We put x equal to a in there, that v goes to 0. You put negative a in there, you have to square the negative a first. Whether you put positive a in here or negative a, you end up having to do the x squared part first. So you get a squared minus a squared. Looks good. So far, so good. Using part E, at what location x will V be maximized? Well, V is going to be a maximum when x is 0. There you go. Let's obtain an expression for V max by plugging part G into part E. We said when x equals 0, you put that in there. What's that going to give you? That's going to give you the square root of k a squared over m. Let me write that down here. V max will equal k a squared over m. What's that equal to? Can I factor out an a? A times the quantity k over m. Substitute an equation we derived earlier into part H. Have we seen this result before? All right, well, if square root of k over m is omega, then V max is equal to a times omega. We have seen that equation before. Perhaps you don't remember, but that's okay. Why don't we real quickly say that, hey, when we were writing equations for simple harmonic motion, this was one of them. This was the one for velocity. And we said, hey, the sine has a maximum value of 1. So the maximum that V can be has the magnitude omega times A. Look at that. That's what we just got right there. That looks pretty good. Let's finish up with a little bit of fill in the blank. When we maximize the stretch or compression of a spring, we maximize the elastic force exerted by it in accord with the equation of Hooke's law, which is F elastic is equal to opposite kx. And for a mass spring system oscillating in simple harmonic motion, a maximizing of this force will cause a maximizing of the mass's acceleration, according to the equation of Newton's second law, which is F net is mass times acceleration.